Okay, today it's going to be recursion again, but we'll do more challenging problems. Okay, it's mainly going to be recursion on the arrays, but we'll solve only 3 problems. Okay. Okay, let me just go to where I want to start first, and then I'll give you some preview of what we're going to do today. Okay. Right. So last lecture, we talked about this last recursive method here to judge given an array which might be empty if it is sorted. Now, today the first problem we're going to solve is given any array, how can you sort it? Right? It's a different problem here. Used to be given any array, you want to return true or false, whether it's sorted or not. But today the first problem is given any array which may or may not be sorted. If it is not sorted, sort it. Okay, that's the first problem. And the second one is we're going to see, given that an array is sorted, we can actually have a very efficient searching algorithm, which is called binary search. Okay, it's greatly improved the performance that we talked about before, as opposed to linear search. And the third problem I would like to go over is called the Tower of Hanoi. You may have seen that already. I want to use that example there to show you how you can compute or calculate the running time for recursive method. That's also important. Okay? But the Java implementation for Tower of Hanoi, I'm not sure if I can get there, but that one's very interesting as a case study. That one's challenging, but it's good. Okay, now let's start with this one here, sorting an array. So now here the problem is sort an array into non-descending order using the selection sort strategy. So here I'm being specific, something called selection sort. By the time you graduate from this degree, you should learn at least the following sort: selection sort, insertion sort, merge sort, quick sort, bubble sort, and heap sort, at least 6. Okay, but for this course, only teach you one of them. Okay, to get some idea how we can do sorting. Okay, sorting is actually quite a well-known problem for computer science. And let's have a look at this. So now, what does it really mean for selection sort? Let me illustrate to you. The idea is very simple. Selection sort simply means you keep selecting until your array is sorted. But how do you do that? Okay, let me give you some idea. Let's go to iPad, and then let's illustrate selection sort, and then we'll go over Java code. Okay, let's add a new page over here. Okay, let's just have an array as an example. Let's say we have an array like this, 0, 1, 2, 3, 4, 5, an array of 6 numbers. Okay, let's say it is not really sorted. Let's say 23, 4, 2, and then 46, 1, and then 3, something like that. Okay, how do we sort this into an array? Into a sorted array. Let's think about what so this is the input. Let's think about what the output should be. Okay, how about just imagine mentally? Okay, the size shouldn't change. 0, 1, 2, 3, 4, 5. The first one should be 1, and then 3. Sorry, not 3, 2. 1, 2, 3, 4, 23, and 46 over here. Agree? Given this input here, which may or may not be sorted, the output must be sorted. So this is the output. Okay? But somehow we have to do it in the middle using selection sort. The selection sort is basically based on a very simple observation. Because we say that we're going to sort in non-decreasing order, which means, what does it really mean for a number to be in the leftmost position? What does it really mean? Smallest, minimum, exactly. And what about this one here? Second smallest, exactly. Third smallest, fourth smallest, and etc. Okay? Selection sort is a very simple idea. Basically, I'm going to keep selecting the minimum elements from the array. Every time I select the current minimum, the first time I select the minimum, it must be the absolute minimum for the array. Put it in the first position in the output. And then search through again the remaining array. Search for the minimum. In this case, the minimum I will get is not the absolute minimum anymore. It's only the second minimum. Otherwise, it would have been chosen in the first time, right? And then the second minimum, put it in the second position in the output and keep going. So overall, you're going to run a loop for exactly the number of times that correspond to the size of the array. Every time, choose the minimum from the remaining part of the array. Let's illustrate this. Okay, I'm going to say do the following. Okay, imagine that I'm going to use let's say red to say it's not sorted yet. Initially, the entire array is not sorted initially. Finally, I want to get to all green. So green simply means sorted. Okay, let's try to use. Okay, we don't create any new array. Okay, so we just do. This is something I'll write it down. It's called in-place sorting. In place. So we don't need to create any auxiliary array. Okay. Let's say the first iteration. What do? Imagine that we're going to grow the green area one at a time. And at the same time, we're going to shorten the area for the red one less a time. Okay? Let's see this. Now, for the very first iteration, select the minimum in the whole green red area. What is that? Minimum. 1. Okay, minimum, we know that it is 1. What we will do is, the same array, the same. I'm just drawing separately, but it's the same array. So we still have 0, 1, 2, 3, 4, and then 5, okay? Something like that. And now we know that the minimum is going to be 1 over here. So that means we are marking this area as green. Only this area is sorted, only that one, okay? The remaining part is still unsorted, okay? Let's just fill in the remaining part. The remaining part is something like this. Let me just write it out. Just give you a little bit more implementation-specific information. Because somehow we want to put 1 over here into position 0. The way to do it is by swapping. Okay? So you can think of what used to be in position 0 is 23. So 23 should now become at position 4. So that's kind of swapping. Everything else remains the same. You will see that exactly in the program. So 4 to 46, and then 3. Okay, let's do one more iteration. So now, when we make the selection the second time, we don't have to select from the green area anymore. Okay, we just select from the red area. So now, what do? Now we can say, what's the minimum now in the red area? 2. Good, thank you. Now 2. Let's try to draw it. Hopefully, after the second iteration, you will see the idea. Okay. Okay, 0, 1, 2, 3, 4, and 5. And now, conceptually, you can think of, after the second iteration, the green area has expanded to be 2 elements. And then the red area, which means unsorted, has now shrinked into just 4 elements. In this case, now, first of all, let's see how we can do it. 1 is still the minimum. Now, you can see 4, it should be 2 over here. 2 used to be over here, used to be here. So the way we do it is by swapping them. So now 4 should become over here, right? We simply swap. Okay? 4, 46, 23, and then 3. Okay? Anyone not follow so far? Okay? So rather than completing the remaining iteration, let me show you the second last iteration. Okay? Of course, after the last iteration, you're going to have exactly just the green array. Okay? That's the last one. Okay? What about, let's have a look at what's going to be the last one? The last one, the second last one is going to be something like this, okay? So we still have something like this. 0, 1, 2, 3, 4, and 5. So what does that mean? That means basically what we have is the green area should be exactly 5, of size 5. And then the red area is basically just like that, okay? So now in this case, the green area, let me just fill it in. So that should be exactly 1, 2, 3, 4, and 23, and then 46. And then once you get to the last one, choosing the minimum from that is trivial, right? Choosing the minimum from an array of size 1, just trivial, okay? Any question about this? And then I'll give you some idea about the running time. Hopefully you can see that. Let me summarize what's visually speaking here. We started with an array which may or may not be sorted. We simply assume it's not sorted. So we say the entire array is not sorted, so entire array is marked as red. In each iteration, we'll make one single progress, which means we select the minimum from the red area, and then use that to expand the green area. So that means we are selecting the minimum, second minimum, third minimum, and etc. That's selection sort. Now, what would be the running time for this based on what we are trying to see over here? Okay, what will be the running time? Linear only in the sense that we're going to do linear time of selection. But what about each selection? How expensive is each selection? First of all, in this array over here is of size 6. That means we're going to select 6 times. But what about the cost for each selection? That's a critical part. Is it constant, really? Are you sure? And log n, not that complicated. Not that complicated. N squared is right, but why, right? Okay, let me give you some idea. Okay, how about, I'll give you a hint. Let's compare the very first selection where we got minimum 1. Is that more expensive, or the very last selection over here, which is only 46? That's another minimum selection. Which one is more expensive? First one. And the first one corresponds to how large the array is, right? Now it's size 6, so that might be 6. If that's n, it could be n. So now let's see. Then you will see some very familiar arithmetic sequence over here. So now the first time over here, n. Big O of n to select. You know what? Let me just do a little bit more pattern-based. So for the very first one, you will have n to select first minimum. Okay, what about the second iteration? n minus 1, exactly, because now the area of the red has shrunk to only n minus 1 elements. So that'll be n minus 1 for the second one to select the second minimum. Okay, now, and then you can see that over here, it will be only 1, cost 1, to select. In some way, that's the maximum, right? In the select, the last time, I'll say, the last time. So now, how many times? So when we add up all these costs together, it would be n plus n minus 1 plus all the way to 1. And we know that very well. That would be big O of n squared. So selection sort is easy to understand, but it's costly. It's n squared. Okay? But in 2011, you'll learn about 2 n log n sort. One is called merge sort, the other one is quick sort. You'll learn about it. And heap sort as well. That's also n log n. Okay, 3. Okay. Any question about the running time for this? I just want to give you some intuition. Okay? Okay, now how do we do this in Java code? Especially, I want to use this as some interesting case study for recursion. Okay? You can see this, the interesting bit about this one is we're going to combine iteration and recursion together. Okay? Think in this way. The iteration happens at the top level. We are trying to do n times selection, right? We're going to do selection 1 to find the first minimum, selection 2 to find the second minimum, and selection n to find the nth minimum, etc. Now, every time when we are trying to find out the minimum, that one I make it recursive. Okay? Now, let me just do another pad to show you. But hopefully the overall picture is clear to you. Let's just do another paper. Okay? And then let's see how we can find out the minimum recursively. That's another problem. And then we combine these two solutions together. Now, problem for you, think about it. This is a problem. Recursively find minimum from an array. Okay, over here. Let's assume a.length is larger than or equal to 1. Let's assume that's the case. So now we're defining something like that, like a find minimum, and then integer array a. Okay? Let's say this is the method I would like you to define, and then it's going to return some integer. Okay? I'm going to show you the code in just a moment, but let's think about the idea. That if you want to solve the problem recursively, think about what a subproblem is. You want to delegate to your friend. In this case, let me draw something over here. Let's say A is pointing to this array over here. Okay? And then we have 0, we have 1, all the way to a.length minus 1. Okay? That's in general. Now, question is, what's the base case? Base case. Let's solve the easy problem first. What's the base case? Length 1, right? In length 1, what would you return? Just the first element, right? Very good. Okay, let's think about the base case. So I'll write it down very quickly. So base case, in this case, a.length is simply equal to 1. In this case, you just return a0. That one's easy. Okay? Now, what about when the length of A is larger than or equal to 2? In this case, how can we split the original problem into some subproblems and then somehow combine their solutions together to make the solution to the original problem, right? That's how you solve problems recursively. Any suggestion? Any suggestion over here?
So once we figure out the minimum, can't we just take it out of the array?
No, actually, you know what? Let's not worry about that because for this problem here, it's very simple. You don't need to take out anything. Okay? You don't worry about any swap. Right? We'll do the swap a little bit later, but not at this stage. Okay? It's a simple problem there. We just want to figure out the minimum in this particular array. But how can you solve that recursively? How can you find a smaller subproblem first? The original problem, what's the size? It's a.length. You want to have a smaller problem. What can be the size of the smaller problem? Let's say that again. I don't quite. Okay, so what you're suggesting was, so the suggestion was as follows. You somehow want to check 0 and 1 to see which one is smaller. As a starter, and then? It's not quite there. You're getting somewhere. You definitely have to make use of the first elements. Yes?
Can we use double recursion?
Double, what do you mean double recursion?
To find the smallest element in the array and then another recursion to like sort it out.
You don't have to sort. Again,
Okay,
don't
so
get.
to find the smallest thing, we just do a recursion here. That
Recursion on what?
the first one is small.
Mm-hmm.
We just want to check if there exists another one in the array.
But where is that another one come from?
Subarray.
Subarray, okay, getting somewhere. Yeah, can.
Just the min of the first element in the remaining part.
Aha, okay, I heard that, okay. Do you want to say something? Okay? Okay, basically what, but both of you said are definitely on the right track, and that's correct. Okay, here's one way to do it. Again, think of this way. Think of the green part is what you can delegate to your friend. This part is simply way too large for me to solve immediately. So this is a subarray of size a.length minus 1. And then I can simply say, this part here is I have control over only the first elements. Okay? So now what I can do is I can pass the green part to my friend. And then I can simply, remember what we said before? For efficiency reason, we don't really create any new array objects. We simply use a from and to. We're going to see this a lot, throughout the lecture today. So you can think of, we have something called find minimum helper, for example. And then over there, the same array reference over here, call by reference, remember? And then over here, we're going to say, now, rather than starting from 0, because 0 can be taken care of by myself. I don't have to bother my friend with that. I can simply say from 1 until a.length minus 1. It's a helper method. So this is going to return back to me some minimum, but it's only the minimum from the green part. But I want to find out what's the minimum for the whole array. In this case, I have to also take the orange part into account. So what should I do? So now there are two cases, right? Either if the orange over there is actually, let's say, less than the minimum in the green part. So that means the minimum is the orange. Make sense? Otherwise, it's the green part. Okay? No, I'm trying to compare the orange and the green and see which one is smaller. In the case where the orange is smaller, of course, the orange should be the minimum. Otherwise, the green part should be this minimum. Okay, let me give you one example. Okay, but I always like to talk about the abstract idea first. Let's see one example right away. Okay, let me give you two cases. Let's say one case over here. Let's say 1, 2, 4, 23, 6, and then 46, 2, and then 6. So in this case, we know that the orange part is simply here. And then I can only do that part, but I can delegate the green part to my friend. In this case, what's the minimum from the green part? In that case, it's simply 2, right, recursively. I know that the minimum is 2. Now I compare 1 and 2. I know that 1 is smaller, so 1 should be the minimum I get. Okay, let's see another example. Okay, let's have a similar array over here. Let's say not too many elements. So now let's say 46, and then 2, 3, 5, 1, and 6. Now in this case, we still split the array in the same way. Let's see how the computation is going to be a little bit different. Here, still the green part to my friend, and also over here, myself. In this case, what would be the minimum from my friend? 1, right? 1 over here. Now, compare 1 with 46. Now, which one should I choose as a minimum for the entire array? 1. Thank you. Okay, you can see the two cases over here, right? Okay, so that's how you can recursively find out the minimum for the array. Okay, we're going to use this as a helper method for selection sort, because we're going to keep selecting the minimum. Okay. Now, when you see the Java code, it's a slight variance to this method here. You can see over here, when we return the minimum, we just return the value of the minimum. For example, over here. When I return the minimum over here, I simply return the value 1. Here, I just return the value also just 1, just a value. But now, in the selection sort, which I will just show you in one moment, we want to return not the value itself, but the index of that value. In this case, we know that 1 has the index 0. So 0 is what we want to return. You will see why, because we want to swap. Remember in the selection sort, I said we're going to swap. That's the trick. And in this case, even though it's only 1, but we're going to return the index, actually 0, 1, 2, 3, 4, 4, right? So that's index 4. So that's what we will return. Okay, so that's a slight trick you have to notice. So it's basically the same problem here, but rather than returning the minimum value, we want to return the index of the minimum value. Okay. Before I take any question, why don't we have a look at the code very quickly, and then you'll see. So let's see selection sort. Okay, you can go over this you can go over that yourself. I already illustrated that. So this is how you define selection sort. Let's say we define this get minimum index, not get minimum. Okay, given an array and then from and to. Okay, we'll simply say if from is equal to 2, that means it's a single array, just single-sized array. We assume empty array is not possible. And then if it's simply a single array, it just return the from, okay, just the index. And then if you have, and then you can recursively call the get minimum index on the tail, in which case you just from plus 1, right? That's how you shorten the range to be compared. And then let's say this is minimum index of the tail. And then you simply just compare the from index and also the minimum of tail index to see which element, which of the associated element is smaller. Whichever is smaller, you return that particular index. Okay? Any question about this recursive method here? Hopefully you are more comfortable with from and to, right? Since we spent quite a bit of time last time. Okay, so this is a recursive method. But now, how do we actually use this recursive method as part of the routine for selection sort? So that's how you can, that's why you will see that we're going to combine iteration with recursion. First of all, we got something called selection sort. Overall, we only give an array A. Okay, that's how the client or the user calls your method. And then we say that if the array is either empty or of size 1, nothing. It's already sorted. You don't need to do anything. And then otherwise, we run a loop. And the number of times we're going to run a loop correspond to how large the array is. Right? We're going to keep selecting minimum. You can see that we can say minimum index is equal to get minimum index. So this is a call to the recursive helper method to get a minimum index. Okay? And you can see every time, you can, one thing to note, I is a loop counter, which would be 0, 1, 2, 3, 4. When I is equal to 5, for example, that means we're going to choose the minimum starting from index 5 until the end of the array. When I is 0, that means we're going to select the minimum from index 0 until the end of the array. So depending on what I is. Once we choose the minimum index, now what should we do? Swap, right? So now we'll simply just swap. Let me just show you again. Remember in the original illustration over there, you gotta do swap. For example, you gotta swap 1 over here with the 23 over here. So once you get a minimum index over here, which is 4, and you're gonna swap A4 with A0, right? That's just how you can do it. Okay, and then that's how you do swap. Okay, hopefully you wouldn't have any problem with doing a swap. Okay, you just need some intermediate temporary variable. Any questions about select and sort? This is the only sorting algorithm we'll cover in this course. You'll learn many more in 2011. Yes? No, it's not necessary. It's just because the way I gave you the sample code, I just have something, a class called like a recursive methods. So it's just why I make everything static. It doesn't have to be static. Guys, any questions? Yes?
Is there an easy way to find the minimum?
Easy way? What do you mean easy way? Yes, you know what? In some way, you're right. For this particular problem here, to do selection sort in general, you wouldn't really use the recursion to find a minimum. You're right. You might just use a loop. But in this case, I just want to do demonstration to show you how you can find a minimum recursively.
Which one is more expensive?
They're equally expensive. Equally, yeah. We'll talk a little bit more about running time for recursion. So I will give you some idea how you can figure out running time. But again, it's only an introduction. You'll learn more in 3101, 2011. Yeah. But that was an absolutely right observation. If I didn't say how you should implement selection sort, even myself, I will most likely do a for loop for selecting the minimum index. But for this case, I just want to illustrate recursion. So it depends on what I need, right?
Are there some problems that you can't do with a for loop and you need to use recursion?
I would say, in general, you shouldn't say recursion is more expressive than for loop. It's just more convenient for some problems. It's a good question. I'll try to think about it, right? I think there's some occasions there, it's actually easier, more convenient for you to use recursion as opposed to loops, and vice versa sometimes. But you wouldn't say one is more expressive than the other. They're equally expressive, right? Mm-hmm. Otherwise, if one is more expressive, why don't you just use that one throughout, right? Yeah. It's a little bit like linked list versus array, right? Yeah. Okay, guys, any questions before I move on to the next one? Next one is going to be interesting. So now, at least you know one way to sort the array using selection sort, and it's n squared time. It's quadratic. Okay, it's not too bad, but still, we're going to learn about something which is n log n in 2011, which is much better. Okay. Now, the next problem there is something like this. Binary search. Okay, let's just go over the searching problem in general. Okay, so there are basically two fundamental problems in computer science. One is called sorting problem. Given any array or sequence, sort it into order. Another one is called search. For search means given any collection there, you want to search something from that. So these are the two fundamental problems, right? So now let's think about what the searching problem is, and then I'll give you some intuition about binary search. And we have to link this back to hash table, okay? Now, so basically you're given a number A, which means something you want to search for, and then some sorted list. In this particular binary search, there's a fundamental assumption we make. I will try to ask you later, okay? I wouldn't tell you why, but let's say we make the assumption that the sequence or the array we are given is already sorted. How do you sort it? You can use selection sort, for example. It's already sorted. And then, what's the output? It's going to be either true or false. Simple, true or false. True if the input A exists in the input sequence. False if A does not exist. True or false. Okay? Now, let's think back to the motivating problem for hash table. Remember I demonstrated that if you got an array, if you simply don't do the hash table way, what would be the time to search through? N, linear, right? So depending on how large the array is, if the array has 1 million elements there, you might take up to 1 million iterations to find out where the element is. Because in the worst case, the element might be at the end of the array. Okay? That's linear, which is very bad. Now, let's say we can make the assumption that the array we are looking at to search on is actually already sorted. So why can we actually improve the performance drastically? Why? Okay, let's have a look. Okay, I'll give you an idea. Okay, let me just illustrate again. Let's go back to iPad. The algorithm itself is actually not too bad. It's not too difficult to write in Java. So I'll focus mainly on the ideas. Okay, so now let's say this. Let me just review very quickly. Unsorted array. Unsorted array. Let's say we have 0, 1, all the way up to maybe, let's say this is how big the array is. Okay, and then let's say we are going to search for, and let's say this is A. This is A. Search elements, for example, let's say 3, and then in array A. Okay, let's say 3 happens to be here, right? Let's say the array contains no duplicates. In this case, it's simply unsorted, so you gotta go all the way, first iteration, second iteration, and all the way to over there. You can only find it in this last iteration, right? So that's big O of n. That's what we said before, okay? Now, let's have a smaller example for sorted array, and let's get the idea. Sorted array. Let's say it's something like this. Okay, let me make it a little bit big. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Well, not too big, just 10 elements. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. A over here. Let's say we want to search for also the number 3, the same ID, the same input, and then A. Okay. Now, of course, for this particular example, you might say, oh, I can still do a linear search because it's the third element. No, that's not the point. Okay. The point is, now, let's do the search from a different starting point. Rather than from the beginning, let's start from the middle. Okay? What do I mean the middle? You can see that this is the beginning index. This is the ending index. Adding up together, which is 8, divided by 2, 4. Now, let's now look for, 9 element, that's correct. I'm just saying, how do I figure out where the middle element should be? I just say the minimum index plus the maximum index divided by 2, right? So I got index 4, right? I just do index 0 and 8, right? Yeah. So, well, actually that makes sense because you got 9 elements and this is the 5th element, right? So that's in the middle. So you got 4 elements before that, you got 4 elements after that. So that's the middle. You just do the index. Indices add up together and then divided by 2. Yep. Okay. So now, apparently, you can see that over here, 5 is not equal to 3. So where should I go? Okay. I can see you guys are, well, for those of you who don't know about binary search, I really want you to think. Now, can you give me any logical reason why can I go to the left without worrying about I might miss 3, which might be on the right? Why would I not miss anything? Only for those of you who did not learn binary search before. Okay, but you can answer, that's fine. Go ahead. It's already sorted. So what does sorting property guarantee?
That the number you're comparing to is larger than the number you're searching for in the leftmost path, and the number is smaller than the rightmost path.
Good. Okay, let me just try to elaborate that. Okay. First of all, the fact that, so that's why this assumption here is very important. You can only do this binary search when the array is sorted. I will show you how disastrous it might be if you do binary search but the array is not sorted. Okay, I will show you at the end. Now, in this array here, because it is sorted, now you can see that the element we are, first of all, if you see the middle element 5, okay, so what's the property for all the elements to the right of 5? What's the property? They're all greater. They're all greater, right? Because otherwise it wouldn't be sorted, right? And also similarly, all the elements on the left to 5, they are smaller, right? That's what a sorting property will guarantee. So now, think about this. We are looking for 3. 3 is not equal to 5, but we can know more about it. 3 is actually smaller than 5. In this case, if 3 ever exists in the array, where should it be? The orange or the pink? Orange, right? Because 3 is smaller, so it's got to be in the orange part. It's got to be. Okay? So now we can shorten our search space. So now this is now the new search space over here. This is a new one. Okay? And now one thing to note, how much smaller is this search space compared with the original one? N over 2. Yeah. Huh? Yes.
Twice as small?
Well, half, right? Yeah, just half. Yeah, that's easier. Well, twice as small, I'm not sure.
Some people are like
Yeah.
against what everyone else says.
Yeah, that's fine. That's fine. Okay, that's basically half. The used to be the orange plus the green plus the pink used to be the original problem. But now we shorten the search space to be just the orange part, which is exactly half. Okay, so now let's see this. Now in this case, we're going to find out the middle elements. Even though we got 4 elements here, the way we figure out the middle is the beginning index over here with the end index. Okay. Now in this case, what do? 0 plus 3 and then divided by 2. We get 1. Okay. Now in this case, the middle element is just 2 over here. That's the middle one. And then we compare this with 3. Also, this is not equal to 3. But now, should we go to the right or to the left? To the right in this time, right? Why? Because we know that 3 is not equal to 2, and 3 is larger than 2. If 3 ever exists, it should exist to the right of 2. Otherwise, the array is not sorted. Right? Now, in this case, we'll simply go to the right. Now, what we have is, we now shorten our search space even further. Even further. Let me use a different color here. How about here? So this is a new search space, like over here, the pink one. Okay, so now we want to find out the middle elements over here. In this case, 2 plus 3 divided by 2. We get 2. Okay? And now this is the middle element we're looking for. And yes, equals to 3, so we return true. Okay, guys, make sense? Okay, basically the way binary search works intuitively is, I'll draw you a tree, even though we'll talk about tree next week. I'll show you intuition about tree. Every time when you try to make a move, either to the left or to the right, you're basically truncating the search space by half. Okay, and then we'll talk about running time in just a moment. Yes. Which one? Oh yeah, of course. The question was, when we were in this particular search space over here, the pink one, the starting index was 2. The ending index was 3. The way we figure out the middle index is by adding up together, divided by 2. So 2 plus 3 divided by 2, you get just 2. We do integer division, right? So that's why you get 2 over here. Okay, you will see that in the code. Okay, now, I want to illustrate to you very quickly what would happen if the array is not sorted. What can go wrong? Very easy to illustrate. Let's say over here, binary search on unsorted array. Unsorted. Okay, let's have something over here. Let's say we are still looking for 3 over here. Let's say everything else was sorted. Okay, 0, 1, 2, 3, 4, 5, 6. Okay, according to binary search, we should find out the middle elements, right? So now in this case, the beginning index is 0. Ending index is 6. 0 plus 6 divided by 2, we get 3. So now that means this is the middle element we're looking for. Okay, now 7 is not equal to 3. Of course, we are doing search, binary search, and then we're looking for element 3 in this array over here, right? According to binary search, 3 is not 7, so which half should we go? According to binary search, not according to the diagram. We go to left, right? Because we assume the array was sorted, but it's not. So I'm trying to illustrate to you what will go wrong if the array is not sorted, but you still apply binary search, right? In this case, you can see that according to binary search, 3 is less than 7. That means if 3 ever exists, you should go to left half. In this case, over here, what you would go is over here. You can see that will actually give you the wrong answer because 3 simply does not exist over here. So that will actually give you false, right? Which is wrong. Because 3 should be here, but it's out of order. It's not sorted. Guys, any question about this simple illustration? I want to show you that. Which means when you do the binary search as a method, you should do a precondition check. I didn't do it in the sample code, but you should do it. Okay? To say the array must be sorted. That could be a nice lab test question. That could be. Or a final exam question. It could be. Either way. Any question about binary search? Yes.
So when an array is sorted, it's always in ascending order?
I would say typically that's the case. Well, it could. It's a good question. The question was, when we say the array is sorted, is it always the ascending order? I would say typically yes. But if the problem say it's actually in the decreasing order, in that case, binary search will still work. You just gotta do it the flip way, if you see what I mean. Okay, let me try to see that. Okay, that's kind of interesting. That can be also interesting final exam question. You know, it's actually very interesting. I'll tell you how you can think of it. Okay, how to do binary search if the array is sorted in, let's just say every element is unique. Let's make it a little bit clearer, okay? In descending order. Okay, descending rather than the ascending order. Okay, before we figure out a solution for this, why don't I show you the source code for Java for the ascending order? Then you have more idea how to do it, okay? I'll come back here in just 1 minute. Let's have a look at the source code for binary search very quickly. It's actually quite easy. Okay, we do binary search, and then you can see I make the name explicit. The array of integer must be sorted, but you should really try to add some precondition to it. Okay, that will be an exercise for you. Array should be sorted, and we have some key to search for. And the way we do it is by calling some helper, and then we say search space should be initially from 0 until sorted at length -1. Okay, just as before. Now, how do we define this recursive helper method? So we have sorted array, call by reference, from index to index and the key. Okay. Now let's see how we can do it. It's actually quite easy. So now, first of all, if the array is empty, we should return false, right? Because you cannot find such element for sure if the array is empty. Now, in the case where the array simply has one single element, you simply compare that element with the search key. If they are the same, find it, true. If they are not the same, false. Okay? Guys, follow so far? Okay. So now, what you really want to pay attention to is to really get used to this from and to indices pattern, because I might give you some, I'll give you some exercises extra for you to practice. It's really important. Now, let's say the middle one, you can see from plus 2 divided by 2, right? That's how we figure out the middle index, okay? And then there's a middle. The middle value is sorted at middle index, right? Now what we do is we compare the middle value with the key to see which one is smaller. If the key is smaller, we should go to the left. Otherwise, we go to the right, okay? So now we say that if the key is smaller, then we make a recursive call. Now, be careful here. This is really the key. The same array, but now, why do I say from and middle -1? Why does that mean? Why does that really mean left half? From and middle -1. Okay, why don't I illustrate this very quickly on the iPad? Let's have a look at this. Let's see over here, when we did a binary search, okay? Okay, over here. Now, let's say this with the binary search over here. Pink one. Pink circle, yes, yes. Over here, yes. Okay, very good. Okay, let's say this. You know what? Let me just illustrate this one more. Okay, I think it's really good to illustrate one more time. Let's say over here, this is from, and this is to, and then this is the middle. So that's the middle index. Okay, and let's say we are looking for the key, and this is array A. When we say A at position middle, okay, so we're comparing that with key. Let's say if the key is less than A at middle, that means we should go to left half, right? How do we specify the left half? It's going to be something like this. It's going to be middle minus 1. Minus 1. And then that's how we do it, right? From and to middle minus 1. That's why you saw something over here. From and middle minus 1. What about the right half? The right half would be what? Middle plus 1 to 2, right? Exactly. Very good. So now let me write it down. So that'll be middle plus 1, and then to 2. So which means it's this area over here. You can see we don't include the middle one because the middle has been compared. It's useless already. Okay, any question about this illustration here? Hopefully that's really the key, right? So now you can see that we are trying to play with the from and to indices, a little bit different from what we did before. Okay, that's really important. You will see that when we get to the Tower of Hanoi, it's even more interesting. Okay, we'll get there. Okay, if that's larger, you do this. Otherwise, you just return true. Now, let's get back to the original question. How do we do binary search if the array is sorted not in the ascending order, but in descending order? Okay, hold your answer. Okay, I'm gonna draw some diagram over here, and then we'll see. So now let's say we still actually do, let's say from over here, we also have to over here, and this is the middle. Now let's see, and then we're searching for a key, right? Also key. Okay. Now if I say key is less than A at middle, now where should I go? To the right or to the left? Why to the right? Yes, descending order. If in descending order, that means everything to the right, to the middle, is smaller than that. So that's where we should go, right? So now in this case, yes, then we should go to the right. In this case, you should go to middle plus 1. From here until over here, right? So now, just like that, you can just go there. Okay, I'm just saying that you should make a recursion on that, right? Guys, any question about this? So I think that's a very good question there, just to say binary search can be done on any sorted array. The array doesn't have to be sorted in the ascending order. It can be sorted in descending order as well. But you got to modify your binary search a little bit to say whether you should go to the left or the right, depending on how the array is sorted. Okay? Questions? Any questions? No?
Not unlike an array of strings.
Yes, definitely. Because you can also compare string, right? I think you can say something like string compared to, I don't quite remember the details. You can just look up to see how you can compare string. Yes, you can definitely sort, do binary search on a string. Okay? I want to give you one more intuition before I go to the next problem. Okay? We still have time. Yes, good. Now, I want to show you one more intuition. We're going to talk about tree next week. And then, let's say over here. Let's say we have an assorted array. 1, 2, 3, 4, 5. Okay? The way you can think of it is, we have, okay, let me do a little bit preview. Okay, it's something called binary search tree. Okay, over here, what we have is, this is an array, which is linear. And we're going to learn about nonlinear structure next week. What does nonlinear mean? That means we got 3 here, which is a root, and then we got 2, and then we have 1, and then here we have, you know what? Let me just expand the array a little bit. That's actually easier for me. 1, 2, 3. 4. Okay, and then let's say we got 7 elements. Okay, sorry for changing that, but it's easier for you to see. 5, 6, and 7. Okay, in the linear case, we have 8 elements from 1 to 7. Oh, sorry, 7 elements from 1 to 7, right? And then in the tree over here, we got actually a tree like this. Okay, it's a very quick preview. This is an equivalent to the array above. Okay, basically we are saying the following. You can see over here, we start with the top of the tree, which is over here, 4. Now, you can see 4 is large. Let's say we are still looking for 3. 3 is smaller than that. That means in the array case, we should go to the left half, right? In the tree case, we should go to the left subtree over here. And when we go to that particular subtree, we can truncate the other one. And again, we are reducing our search space by half. I'll try to review this diagram maybe again next week. Maybe it's hard for you to imagine right now. Okay? Yes?
If you're going to make a tree, are you controlled by like linked lists?
Yeah, you know what? Let me save that discussion. I should have even mentioned this actually. Yeah, I thought it might be interesting to compare. But let's save this diagram here. If you didn't get this page here, don't panic. That's fine. We'll get there next Wednesday. Okay? We'll talk about tree next Thursday. Yes, not Wednesday. Okay. Now let's go back to binary search. Binary search. Any question about this before I move on? Okay. Now, Tower of Hanoi. Okay. We have about 25 minutes. I want to go over at least the problem. I want to do several things for this problem here. I want to, first of all, to describe the problem and talk about how you can solve this problem recursively. And then we can talk about the running time and then how you can prove the running time formally using mathematical induction. These are at least the 4 things I want to talk about. And then I will show you how you can implement this in Java. Okay? It's also interesting. Okay? Both. Okay, now, any one of you who has not heard about the Tower of Hanoi? Okay, that's good. That's a nice way to ask questions. That's good. Okay, good. So now, let's say we got 8 disks. Okay, we got 8 disks over here from smallest to largest. And then we got 3 packs, 1, 2, and 3. Okay, let's say we got some convention here. For the disk, we say A, B, C, D, E, etc. For packs, we say 1, 2, and 3. So that's the input you will see in the Java code. Okay, so now let's say you gotta move only one disk at a time, and then never a larger disk onto a smaller one. Okay, you know the rule. Just want to make sure you know that. Okay. Now the problem is you want to transfer the entire tower from one into another. For example, let's say this is pack number 1, this is pack number 2, this is pack number 3. I say I want to transfer this whole tower from pack number 1 into pack number 3, right? That's one way to specify the problem. Okay, just make sure you understand what the problem is. Okay, now how can we solve this recursively? Right? How do we do that? Again, the way you do this is by considering base cases, and then think about what smallest problem you might get, and then combine the solution to smaller problems to make the solution for bigger problem. Right? That's always the process. Okay. So let's talk about the strategy for Tower of Hanoi. Okay, let's talk about it very quickly. Okay, now let's Tower of Hanoi. Okay, I add a page over here. Okay, so now let's think about how we can solve it. Okay, Tower of Hanoi. Base cases first. Okay, the problem is you may have, so now let's just make let's make some convention over here to say let's say we generalize the problem a little bit. Since we're computer scientists, we shouldn't be so bothered by the magic number 8, as I said in the previous problem. It doesn't have to be 8, doesn't have to be 3, it can be 1,000, can be anything, right? We want to generalize the problem. Let's say we simply want to consider the problem of n disks, which means there's a tower of n disks. I want to move that from peg number 1 entirely into peg number 3, okay? Now, let's just have the convention. And now let's say this. We use a mathematical symbol here. So T, which standing for tower. T of n is the size of the tower, right? N disks over there. We say that Tn tells us the minimum number of moves to actually move from one tower, from one peg into another peg. Okay, let's see one example here. So now let's see over here. First of all, what does T0 really mean? T0 simply means we got 3 pegs over here with no disk. In this case, how many moves do we need? 0. Good, good, good. Okay, what does T1 really mean? T1 means we have also the 3 pegs over here, and then let's say move. Let's make the following assumption: move from peg 1 to peg 3. Okay, let's say it's always the case. So this is 1, this is 2, this is 3. Okay, that's the assumption we are making. So now what's T1? 1, right? That simply means, let's say I choose A, B, and C. If A is already here, right? I don't have to work. I don't have any constraints. Simply move from A here to here, just one move. Okay. So this will be move A from 1 to 3, from peg 1 to peg 3. Okay. Let's try another one. What about T2? Minimum. I heard 3. Okay. Why don't we try? So now if you have over here, we got peg 1, peg 2, and peg 3. So now A is smaller, B is a little bit bigger, okay? A and B. Okay? So now, what should we do? Move A to somewhere, right? Should we okay, so move A to 2. And then B to 3, right? B to 3. And then A, 2, 3. Okay, so far so good. We'll talk about, okay, now we can say that these two are the base cases. These are the base cases. They are easy, trivial. T2 over here is not really the base cases, but it's simple enough for us to learn something. But it's not really that substantial enough, so we better do T3 as well. Okay. Before that, I want to show you something. I already encoded this in Java. Let's see how powerful the computer program is. I got Eclipse running here. Let me just illustrate very quickly to you. Okay, if you download the source code, you will see that under recursive methods over there, you have something called the Tower of Hanoi. Okay, I'll go over the code maybe possibly Monday if I don't have time today. And then we got also Tower of Hanoi helper. Okay, let's just see how it can be run. Okay, first of all, if I go to the recursive method tester over there, you can see that at the end. So this is how I use it. Okay, over here. Okay, I simply pass the disks over here. Okay, the disk can be an array of string A, B, and C. Okay, this is we have the following convention. The leftmost is the smallest. So A is smaller than B, B is smaller than C. That's convention. So that's how we simulate a tower. Okay, A, B, and C. So now let me just see if I simply got A and B. Okay, just that. If I run it, let's see what we have. Okay. Oh, console over here. Okay, that's exactly what you guys just said. Move disk A from peg 1 to 2, move B from 1 to 3, move A from 2 to 3. Right? Exactly what you said. Okay. Now I just want to illustrate to you how computer program can be useful. We're going to do 3 altogether manually, but I want to go back there and then I want to show you this. I want to make a small change. Let's say A, B, C, D, E. Okay, just like that. Okay, let's see how many we'll get. Okay, over here, sorry, it's a bit, okay, if I maximize the console, these are the steps. It tells you, you can try to go over that if you want. Basically, these are the solutions. Okay? Basically, you got about 31 steps over there, 31. Yeah, something like that. How do I know it's 31? I'll tell you where. We'll tell you later. Okay? There's a formula to that. We'll learn that. Okay? So that's a solution for if you get 5, A, B, C, D, E. Okay? Now, before we know how to do this, well, hopefully, once you study this algorithm carefully enough, you can also do this. Okay? But let's now learn how we can observe the pattern. That's more important. Okay? Let me go back to the iPad. I think, I kind of forget, I think the Tower of Hanoi, they got some variant to say there's a legend. So inside the temple somewhere, there are 3 monks doing the, how many discs are there? 64. To say they basically have been doing this, and once they're done, it's going to be the end of the world. Something like that. Yeah. But if you see that mathematically, it's never going to happen. Yeah, well, it's going to take a long time, right? Okay. Don't worry, we are safe. We are safe. Yeah. All right, anyway, let's now go back to the iPad, and now I want to do T3, okay? We have done T0, T1, T2. Let's now do T3, okay? Let me just add a page over here, and then we should get an insight into the problem. Okay, T3. Now, T3. This is a problem. Let me start you with the problem. Pack number 1, pack number 2, and pack number 3. Let's say, now, this is A, B, and C. Okay, A, B, and C. Now, how many moves do you need? I have 7, that's good. Okay. But now, let's now, the exact way, exactly how you do it is not that important anymore. We should now think recursively, right? Now, let's think recursively. What can be a subproblem for this? What can be a subproblem? Yes? Okay, I can see what you mean. Okay, let's try. Okay, basically, this is like this. You can think of the following. You can think of the AB over here. We know that A and B can also make a tower of size what? 2. And which is strictly smaller than the original problem A, B, and C, which is of size 3. Now, you can think in this way. Somehow I can delegate this problem to my friend, tell my friend, now move A and B into which pack? 2 or 3? Second one, right? Remember our goal. Let me say that again. Our goal is to move A, B, and C from 1 to 3. This is 1, this is 2, this is 3. That's the final goal. Now, when I delegate this problem here to my friend, I got to be careful. If I tell them to go to the wrong pack, I'm going to solve the problem wrongly, right? So now, I should really ask my friend, they certainly cannot move AB from 1 to 1. That doesn't make sense. They can only from AB, the power AB from 1 to 2 or 1 to 3. Which one? 3 or 2? Okay. I should repeat, yes. So now let's say we have in some way move A and B. Okay, think of it as a tower. Okay, move AB from 1 to either 2 or to 3. 2, right? Because now, this is how you think of it for this problem here. Since our destination is 3, and we're currently at 1, so 2 is more like the intermediate one that we can just buffer. Okay? So now, basically what our friend is going to do is, they're going to somehow put A and B somehow over here. Okay? Temporarily. And then, so now A and B is gone. And then we can put C from 1 to 3. And then after that, we can move A and B over here from 2 and then to 3, right? Okay, I'm going to write it down, okay, in a moment. And this one is going to be A and B. That's kind of the steps, 3 steps actually. Now, let me write it down, and then we'll see how the recursion is called. Okay? So now, basically, there are 3 steps. And you tell me which ones are recursive. Move the tower of A and B from 1 to 2. And then you move the disk C from, because A and B has been moved already, right? So now C is the top one, from 1 to 3. And then, since now A and B is already in the intermediate pack, so we can say move A and B now from where to where? 2 to 3, right? Right? Because it's already 2, right? 2 to 3. Okay, I'll pause a little bit, and I want you to just do one more highlight. Okay, I'll pause a little bit and take questions, if you got any questions. 3 steps. How many recursive call are we making? 2. Which 2? 1 and 3, right? It's quite obvious, right? I can highlight it for you, okay? So now you can see that the first one there, wow, let's see this. If you understand, okay. Let me just make it a little more general for you, and then we'll try to trace maybe a little bit later, okay? Let's make it a little bit more general. Let's say this. If you have T of n over here, if you have 3 packs over here, let's say you have a tower like that, and then it's of size n. How do we solve it, right? The way we can decompose this problem over here is by saying only the bottom one is going to be our job, only the bottom one. And the rest is going to be our friend's job. Okay, I'll try to color carefully. Okay, right? So the red one over there is our job. Okay, so now step number 1. So again, 3 steps over here, 3 steps. And now step number 1, move the green tower over there from 1 to 2. And then you can move the bottom one, which is our job, from 1 to 3. And then you can move the tower, which is already on 2, right? Okay, I'll draw back to the picture in just a moment after I finish the text. From, and then you will say 2 to 3. Okay, now, step number 1, we simply just move the tower, basically, to here. And then step number 2, we move the bottom one into here. And final step, we move the tower back there. Okay, hopefully that is clear to you. Now, we want to see the cost of this. Okay, let's try to learn the cost of that. You can see that. Let me just illustrate to you again, and I will ask you a question. You can see that this is our original problem. This one over here. Hopefully you can see that. That's Tn. Okay, this is a bit bad color actually. Let me use, how about pink? Okay, this is our original problem over there, which is T of size n. So what's the size of the first step problem? What's the size? Tn minus 1, except for the bottom one, right? So this one over here is Tn minus 1. What about the second step? Just 1, right? Because only 1 move, only from the bottom from 1 to 3. Okay, 1. What about the third step? Tn minus 1, again, right? Just from different pack to different pack. Tn minus 1. That's how you figure out the running time for, that's how you define the problem recursively, but we'll get there about how you can calculate that, okay? So now in total, you can see that this is what you will have. First of all, we know that T0 is simply equal to 0, base case. Also, T1 is equal to 1, but it's not really necessary, okay? And what about Tn? We know that it's going to do step number 1, and then plus step number 2, and plus step number 3. Okay? In this case, it's going to be 2 times Tn minus 1, and then plus 1. It's a bit mathematical, right? Hopefully, you can just maybe review the notes. Any questions until now? Okay? Well, first of all, try to argue about the running time for this. We haven't done the running time yet. We want to know how this recurrence relation, we call recurrence relation, right, is going to unfold it into. And then we'll try to prove it. And then we'll see Java code. We'll do Java code last. Okay? Okay. Hopefully, maybe we'll just do the math this time, and then we'll do the Java code next time. Okay? Now, let's see how we can do that. There will be some mathematical part. Okay, let's see that. So this is a recurrence relation we have. 0 and then 2 times the subproblems over there plus 1. Now, this might be, I would say this would be the most difficult problem I might give to you in the test or in the exam, if I were to write an exam, right? Now, let's see this. Over here, let's see how we can figure out the running time for this recursive method or recursive solution over here. So now, somehow the solution over here is indirect. Why? Because, let me just show you an example. Let me just write it down in just a Let me write down the recurrence relation again. T0 is 0. And then we have Tn is equal to 2 times Tn minus 1 and then plus 1. That's what we have, right? Now, let's do a little bit of math, okay, before we get to Java. Okay, it's very easy math. Now, tell me something. What is T of 4? According to this relation, how would you solve it? According to a definition. Okay, let's do step by step. How about that? By definition, we know that it matches either this one or this one, right? Should be the second one. So that means a recursive case. So that should be T of 2 times T of 3 plus 1. And then what's T3? Well, it's going to be 2 times, right? You can see 2 times T2, and then plus 1, and then plus 1. Can you see where I'm going? Okay? To avoid making mistake, you can do the rest. You can see how tedious this is, yeah, okay? But I kind of see the idea, right? Okay, I can do just one more. How about that? Just do one more. Well, how do we continue with that? 2 times, and then something over here plus 1, and then plus 1. What's T2? T1 over here plus 2 times T1 plus 1, right? You still got to continue until reach T0, and then you can add them up together. However, this solution here is, well, not too bad. If you did, well, I'll tell you what, you can either say, I'm happy with this. Then I can say, now solve a T54 for me. Well, I mean, that's too drastic. Maybe T10 for me. How about that? In this case, well, you can feel free. I will give you paper during the exam. But in that case, no, you don't want this. So this is indirect. So what we really want is something called a closed form solution. Okay, I'll show you what that means, which means a single formula. Okay, what we really need is some closed form solution. Actually very easy. Okay, basically, this is what we're going to do. You're going to just do some example over here, just to unfold the, for example, you can see T0 is this. T1 will be 2 times T0 plus 1, which is 1. T2 will be 2 times T1 plus 1, which is 3. Just do a few. Do a number of them. This will be how you will solve others as well, just for this course. Now, and then use your imagination. Take a guess. Oh, I shouldn't show you that, right? So what is that? What would be your guess? Yeah, to the power n minus 1, right? Yeah, that's really bad animation. Yeah, it's really bad. Okay, that's, yep, you guessed right. That's 2 to the n minus 1. Now, guessing the right thing wouldn't lead you too far. You're going to prove it. How would you prove it? Well, mathematical induction. Okay. Let me just use about less than 5 minutes. Let's do the mathematical induction very quick. I got all the details, but let's go very quickly. I want to make sure you know how to do it. So now in the test or in the exam, I'll give you something very similar. What you gotta do is observe the pattern, guess some closed form solution, and prove it. That's what you gotta do.
So, for EECS2030, we learned how to solve the recursion condition.
Oh, you already learned? But I think that for some people there, I don't think they took 1019 before. So I think that this one maybe will be helpful for them. You can use that one if you like. Yes, yes. Okay? Okay, let's just do very quickly. So now, this is the closed form solution we guess. So basically, we're saying that Tn is equal to 2 to the power of n minus 1. How do we prove that by mathematical induction? Well, amazingly, the way you prove induction is very similar to how you do recursion. Base case, inductive case. Let's do that very quickly, and then we're done. Okay? Now, base case, you can simply say T0, we know that it's 0. That's exactly 2 to the power 0 minus 1, right? That's according to the formula. What about recursive cases? This is the format you're going to follow. You're going to assume to say, for a problem of size n minus 1, I got also that answer for the closed form. And then I can use that to actually get a solution for the size n, which will be consistent. Okay, let's see that very quickly. Let's assume T of n minus 1, which is subproblem. And that's actually the closed form solution. That's what we assume. We're going to want to prove it. Now, what do we want to prove? We want to prove that given this, assuming this, we want to prove Tn is equal to 2 to the n minus 1. Right? How do we prove it? Let's try. Tn, by definition, is what? By the recurrence relation. 2 times Tn minus 1 plus 1, right? That's our recurrence relation. And then, by our mathematical inductive hypothesis, we can plug in 2 to the n minus 1 into Tn minus 1. And what else? Use your mathematical skill to simplify that. And hopefully you can get there. Yeah. And then you get 2n minus 1. Okay? Okay. So you can simplify that, right? I will leave that to you. That should be very easy. We shouldn't waste time on that. Okay? Good. Now, what's really useful about this closed form? Now, let's say I give you, what about when n is 8? How many moves are there? Well, you're 2 to the a minus 1. 255. If you try the Java program, it's going to output exactly 255 lines. If I want you to solve the puzzle on the paper, you will need that exactly 255 moves. Okay? That's the beauty of math. Okay, guys, okay. Now, I'm running out of time, so I want to make some remarks about lab tests. And give me one moment. Okay, let me say what you should do by Tuesday, and then I'll stop the recording, and then I'll talk to you very briefly. So now for the Java code, I will go over this next time, but it's already available. Look at that very quickly, and I'll go over quickly on Tuesday. And then we're going to move on to other topics. And then let me stop the recording.